Yeah. We're not going to have a final. We're just going to have a third exam on the last day of class. It's a Friday. It's February 4th, I think, off the top of my head. No. All right, everybody, welcome back. We're going to be talking about volcanoes even more today. Hopefully we'll finish up with this, then Thursday and Friday we'll talk about flooding. Keep in mind, quiz 2 is due at the end of the week on Canvas. Should be on volcanoes and maybe flooding. So I think that'll be open tomorrow at the end of the day. So keep that in mind, put that on your schedule. Yeah. So yesterday we were talking about chemical composition, physical characteristics of magma and lava, and how that affects the type of eruptions and eruption styles that we get. Today we're talking about where those different types of eruptive styles and different types of volcanoes occur and why they occur where they do, and the different types of volcanoes that we get from these different magmas and lavas. So basically, different volcanoes occur in all sorts of different tectonic settings. We have our divergent boundaries over here to the left, where heat's coming up. That ridge push is going to spread the plates apart. New magma is going to enter that void space, that crack in the Earth's crust, and erupt. So most of the eruptions happen there. We have hot spots that come up directly from the mantle. They're super heated spots of magma that can melt the centers of tectonic plates. So we get a couple of those on the Earth. They're not very common, but they're common enough that they're of interest to study. And then, of course, at convergent boundaries, we have subduction zones, that slab pull being pulled into the mantle, melting all those volatiles that are stuck in that subducting slab. It's going to help melt that slab a lot faster, get us a lot more magma, a lot of volatility, a lot of viscosity. So we're going to get more explosive volcanoes at convergent boundaries. So basically, the types of tectonic regimes are going to give you differences in those two key components of pressure and temperature. So obviously, whenever you have pulling apart divergent boundaries, you're going to get lower pressure. There's going to be less stress and less weight built up right at that spreading center. For conduction at hot spots, you're going to get an incredible rise in temperature. Remember, differences in pressure and differences in temperature is what it takes to melt rock. And of course, with convergent boundaries, all it takes is adding volatiles, add a little bit of volatility, you're going to get some type of melt. That'll help change the melting point. 90% of volcanism is associated with plate boundaries. The other 10% is hotspots like Hawaii, the Canary Islands. People believe that Svalbard up near northern Norway is another hotspot, but we don't have enough data there yet. As well as not the Azores. The Azores are at a spreading center, but the Canary Islands for sure are a hotspot. 80% of that volcanism with plate boundaries occurs at our divergent boundaries. We get a lot of volcanism. It's not very eruptive, it's not violent, but the largest portion of that occurs at spreading centers, at divergent boundaries, like the mid-ocean ridge in the mid-Atlantic. You have the mid-ocean ridges in the Indian Ocean as well, next to the India-Australian plate and the Antarctic plate. And then, of course, with our hotspots, we have Hawaii, where we're melting the overriding plate, as well as in the Canaries, where we're melting the African plate. So we'll look at each of these boundaries and how it works. So let's start with decompression and that process. So as we know, at divergent boundaries, those plates are being pulled apart. So as you're pulling things apart, you're creating a release in pressure. You have this void space at that rift where fresh magma can come up. Whenever you're releasing that pressure of that overriding plate weight, you're creating a space where that magma can come up to the surface. So it stays at a high temperature all the way up, but the pressure is changing. So remember this phase diagram where we have that geotherm of that relative temperature as we go down from the surface of the Earth down into the asthenosphere. All that's happening at divergent boundaries is temperature is staying constant, but we're decreasing pressure as we're rising up from the mantle. So we get less pressure, more melting, because we're not compacting, we're not squishing those rocks and making those rocks into solids. We're releasing that pressure, have a little bit more room to flow, to melt. So that's what we're getting at divergent boundaries. So where are we going to get decompression? Based on this map that we've seen hundreds of times in this class, where do we think? Is it A? Is it B? C? How about D? E? General confusion from anyone? Okay, so the answer is D. D is where we have our divergent boundaries. Remember the legend of this map where we have those hatch marks, blue lines, those are divergent boundaries. The plates are being pulled apart. Wherever we have plates being pulled apart, we're going to get that decompression, that release of pressure, and all that magma is going to come up to the surface because there's no more pressure keeping it down. So whenever we have divergent boundaries, we know we have basaltic magma because most divergent boundaries, with the exception of the East African Rift, it happens at oceanic plates. So we have all this deep, dense oceanic crust melting down from basaltic magma. Remember, basaltic magma has low viscosity and a high temperature. If it has low viscosity, what does that mean? Does it have high silica content or low silica content? Yeah, low silica content. Remember, silica is that as those tetrahedron form sheets and chains, that's going to create more viscosity. It's a lot easier to move things that are broken up than if something's formed into a chain or a sheet. So less silica content, low viscosity means it's going to preferentially flow. It's going to come up to the top. It's going to erupt easily. We don't have a lot of volatiles because all of this magma is sourced from the mantle. So we don't have the water vapor, we don't have the CO2, we don't have anything that's going to volatilize that melt more. So instead of getting violent eruptions, we're going to get very gentle, non-explosive eruptions. This is the most common type of eruption that we get. We don't see it very often because obviously it's at the bottom of the ocean. We're not going to see it at all. The moment it comes up, as those plates are spreading apart, it gets immediately cooled down by all that overriding ocean water. So all that happens is that ridge just builds up and builds up over time gently. So that's what we get at these spreading centers. We do get some of this happening on the surface. So to the right, this is in Iceland. Remember, Iceland is situated right along that mid-Atlantic ridge, along that spreading center. That trail right there is the trail between two tectonic plates. To the left, you have the North American plate. To the right, you have the Eurasian plate. So you're able to walk in between these two plates. Also, you have in East Africa over here to the left. Oh man, that's a terrible, terrible picture. But we can still have these at the surface. We don't get a lot of violent volcanism from these areas. As you can imagine, Iceland, they do sometimes get some violent eruptions, but those are from different overriding geomorphic features rather than the spreading center problems that they have. So let's talk about hotspots, specifically how conduction works in order to make hotspots. So in the last one, we had a release of pressure. In this one, we're going to have an increase in temperature. So as we increase temperature, we're going to melt things faster, as you can imagine. That's probably the easiest way to think of to melt things down, is just up the heat. So conduction melting happens whenever we have the heat from the outer core or the lower mantle, the very, very hot stuff, and that comes all the way up. Remember, hot stuff rises to the top, heat rises, cold air sinks. So all this heat is going to eventually rise up as a plume where you have this almost stingray shape in this mantle plume. And it's going to, as it's rising, it's going to melt the surrounding rocks. It's going to bring up and melt the pyroxene, the olivine, all the stuff the mantle is made of, and it's going to bring all that stuff to the top. So in certain cases, if you have, say, like a continent, you can get flood basalt. In other cases, you can get what's known as a volcanic trail, which is what Hawaii is. Remember, Hawaii is that chain of islands, and that chain follows the general plate motion direction. So the hot spot is staying still, the plate is moving over top of it. So it just deposits a volcano, the plate moves, deposits another volcano, plate moves, and so on and so forth until there's no more plate motion or the magma chamber, the hotspot, is gone. But in cases where you have flood basalts, that's where we get all of that magma is coming out all at once. Instead of just gradually over time where we get these volcanic islands, we're getting all of it spilling onto the surface instantaneously. So these are really violent eruptions. It's a lot of magma covering a large, wide area. One of these flood basalts was one of the main reasons we had a mass extinction event in Siberia. The Siberian traps are a massive flood basalt. I want you to imagine a volcanic province the size of probably Pennsylvania. Just imagine the entire state of Pennsylvania covered in magma. That's what these are. Flood basalts are huge, enormous, enormous places that bring magma up to the surface. So they're pretty crazy. All right, so where on earth are we going to get conduction or heat melting? Just shout it out. A, right? A is Hawaii. It's the center of the plate. It's not at a plate boundary. So that's where we're going to get our hotspot volcanism. That's where we're going to get conduction and heat melting to form magma. Anywhere else, we're going to get different types of preferential melting rather than just bringing up a huge plume of magma from the center of the earth. So as we mentioned, since all of this is coming from the center of the earth, we're not going to have those volatiles again. Remember, volatiles come from the surface. As we're melting stuff down from the surface, that's where the volatiles are coming from. That's what's going to accelerate the melting. But these are still pretty gentle eruptions. They can be large in scope and shape, but you're not getting a Mount St. Helens, for example. So since Hawaii is one of the best examples, think of Kilauea. Kilauea and Mauna Kea are the best textbook examples of hotspot volcanoes, just because they're shield volcanoes, cover a wide area. They don't build up very high. They don't explode and send huge columns of ash spreading over the Pacific. They're just very gentle. Eventually, they get road closures on Hawaii just because of all the lava flows, but it's more of an inconvenience than it is a huge disaster. So Hawaii is an example of a hotspot in an oceanic plate. The Canary Islands are in a continental plate, but they're still in the ocean. Can we get hotspots that melt down continents? Because remember, continents are made of those felsic rocks. They're much lighter, so they float on the surface. They build up a lot thicker. So the continental crust is a lot thicker. So can we develop enough heat to melt down those thick crustal layers? We can. The best example of this is Yellowstone. Most of you have probably heard of the Yellowstone supervolcano. It comes up in the news every so often whenever there's some type of seismic event or some type of shift in the Earth's crust. Everyone talks about the supervolcano and how it's going to explode and kill us all. It could explode. It could also not explode. It's over the period of 2 million years. It has erupted 3 times. And while we could calculate the recurrence interval from 2.3 million years ago to 1.3 million years ago to 640,000 years ago, that recurrence interval is huge. It's drastic. I think that's a recurrence interval of 1 every 750,000 years, 700,000 years. My math's probably wrong there. But still, it's a huge amount of time to have an explosive eruption at Yellowstone. So most of that pressure that's built up in Yellowstone is being released by the geysers. If most of you have probably heard of Old Faithful, that geyser that would erupt at timed intervals. It is not so faithful anymore because there was some seismic events and now it doesn't erupt at the same timed intervals anymore. But you still have that constant release of pressure beneath the tectonic plate from all of these geysers, releasing those volatiles, releasing those gases. But the interesting thing that you get at continental hotspots is that you get what's known as magma evolution. You have basaltic magma coming up from the Earth's core and the mantle, where we're getting our olivine, our pyroxene, all our heavy, dense rocks. But as we're heating up, that overriding plate of the continental lithosphere, that's going to melt too. So that's our rhyolitic, our felsic magma, our heavy, highly viscous stuff. A lot of silicon content. Remember, felsic, Si, and felsic stands for silicon. We're going to have a lot more silicon content. So the concern with the Yellowstone caldera is mainly because you have this overriding magma made of felsic materials. If we have felsic magma, we're going to have more viscosity, and more viscosity means we could potentially have more violent eruptions. That's why Yellowstone at the current state is a caldera. At one point, 640,000 years ago, it had a huge eruption, so huge that it collapsed into this crater that you see today. And we're going to talk a little bit more about calderas and how they form in a little bit. All right, now let's talk about convergent plate boundaries. Now we're going to add volatiles to the mix. So instead of changing the heat, changing the temperature, we're going to do a little bit of that as well as we're pulling the slab into the asthenosphere. But what's going to start to agitate first is all the volatiles in the rock. Rocks are really hard to melt. It takes a lot of pressure or temperature to drastic changes in pressure and temperature to melt rocks. But it does not take a lot of energy to agitate or disrupt volatiles like gases, water vapor, stuff like that. You can put water on your stovetop, and at 212 degrees Celsius, Fahrenheit, it's going to boil. As you can imagine, as we get into the asthenosphere, it gets a lot hotter than 212 degrees Fahrenheit. So it's going to be a lot easier to help melt that rock surrounding it if we have a lot of water vapor, a lot of CO2 built up inside the subducting slab. So as we're pulling this slab in, volatiles are going to help melt down that rock. It's going to travel upwards, and because it's this is the primary melt, the melt's coming from the subducting slab. As we're coming up through to the continental crust, we're going to get secondary melt from the heat from that melting magma coming up. It's going to melt the surrounding continental crust. Remember, continental crust, more silicon, a lot of viscosity. So this is where we get the most explosive eruptions, incredibly explosive eruptions. So andesitic magma, remember andesitic, named for the Andes. This is where we find these types of volcanoes, where we have the oceanic crust subducting under the continental crust, a lot of volatiles, a lot of viscosity over top from melting the lithosphere, and that's where we're going to get our really explosive eruptions. That buildup of pressure because of the viscous magma on top, and the buildup of gases below that viscous layer, that's where we get our explosions. All right, so those are the three different tectonic settings that we can get volcanic landforms. Let's talk about the landforms themselves. As you can see, we have a bunch of different types. We have down here at the bottom left, that's a stratovolcano. That's your, whenever you picture a volcano in your head, you're probably thinking of a stratovolcano. High, steep peaks, crater in the middle, spewing lots of ash and lava out of the top. We can also get a Palaeon eruption, where we have more layering, not huge columns of ash, but we still get some ash, a lot of lava flows. We can have two different types of shield volcanoes. Hawaii is a shield volcano. We also have Icelandic shield volcanoes. Those happen more as like fissures or rifts. So they're more linear features than they are round features. Then we have cinder cone or strombolian eruptions that we'll talk about in a bit. Each of these are pretty complex and they form based on the 3 V's. Remember, viscosity, volatiles, and volume. All right, so if we have low viscosity, low volatiles, meaning we have low silica content, so we don't have any viscous layers. We're not getting anything from the surface, so we have low volatiles, but we have a lot of it. Think of a hot spot. That's where we get shield volcanoes like Hawaii. Huge volumes of lava, but not very eruptive. That's where we get shield volcanoes. That's why they spread out over such a large area, but that's also why they don't spread up really high. Very thin lava, it wants to spread out laterally, not vertically. Same thing with a flood basalt, except we're gonna up the volume even more. Huge volumes of lava. It's gonna spread out over an even larger area. That's why it's called a flood basalt. Acts as if it's a flood of lava. But similar to a shield volcano, similar in structure, spreads out over a large area. So let's move to stratovolcanoes. We're going to increase the viscosity. We're going to increase the volatile count because this is happening at a subduction zone. And we're also going to have a lot of volume. That's why we're going to be able to build up so high, but that viscosity is going to also enable us to build up vertically. And that's where we get our most violent eruptions. High volatile count, high viscosity. Buildup of gases and something holding those gases back. And then calderas at the bottom here. High viscosity, high volatiles, and huge volumes of lava. That's where we're going to get the most explosive eruptions, and that's why we're going to get a collapse of that volcano after each eruption. All right, so here we have stratovolcanoes. This can be andesitic, so we're forming at convergent plate boundaries, subduction zones, subduction of an oceanic crust over underneath a continental crust. We're going to melt down the felsic rocks on top, build up that viscous layer, and we're going to pile up over and over as we build up this mountain of this volcano. This is where we get a lot of pyroclastic activity. We're getting those not so melted rocks spewing out of the mouth of the volcano. We're going to get a lot of ash. We're going to get a lot of gases coming out of the volcano when it erupts. But these eruptions are propelled mainly by pressure. As the volatiles are agitating and they're building up beneath the viscous layer, they're going to explode based on that buildup of pressure. Think of a champagne bottle. So a stratovolcano, we call it a stratovolcano because it has strata or stratum, which are these different layers of ash, pyroclastic material, lava flows, because with each eruption, it's going to erupt over the side of the volcano. As it cools down, it creates a new layer, and it keeps going like that over and over and over again until we build up the volcano to what you see today. So this is an example of what Mount Rainier looks like, which is a stratovolcano. Mount Rainier has erupted in the past. It hasn't recently, luckily, because it's very close to huge population centers. But what we also get at stratovolcanoes is we get vents. Liquids always follow the path of least resistance. So if it can, rather than coming up to the center, if it can find cracks or faults within the sides of the volcano, it's going to preferentially flow that direction as well. So we can get some side eruptions, and this is how we get eruptions like Mount St. Helens, where there was just like a collapse of the side of the volcano and it erupted sideways like a shotgun blast. So really violent, and it had a directional component too. All right, so where would we have a stratovolcano? Think of high amount of felsic magma, buildup of volatiles. Where are we going to get those types of volcanoes? Who can tell me? D. D is a conversion plate boundary. We have the Nazca plate subducting beneath the South American plate. We're going to melt those felsic rocks above, build up that viscous layer. The volatiles in that subducting plate are going to build up beneath the viscous layer. That's where we're going to get our stratovolcanoes, our explosive volcanoes. All right. I forget how long this is. And obviously you guys can't hear it. So we're going to skip that. All right, so with stratovolcanoes, we can get something called a Plinian eruption, which is a different type of eruption. It stems from, its etymology is from Italy, specifically from the Romans, where we have Plinia. We measure volcanoes on a similar magnitude scale to earthquakes. It's called the Volcanic Explosivity Index, VEI. So for Plinian eruptions, we can get ranging from a 4 to 6, pretty high on the scale. So we have high viscosity lavas. They're not going to flow over a large area because they have a more viscosity. They're going to resist that flow. So they're going to build up near the mouth of the volcano. Very explosive. And we're going to have huge, huge ash clouds and huge columns of ash that'll spread over a large area. So in the example of Mount St. Helens, we had huge pyroclastic flows, that avalanche of ash, of rocks, of semi-melted rocks, and hot gases flowing down the side of Mount St. Helens. At the same time, we had this huge ash cloud that spread over most of the United States. You can see these ash deposits from Mount St. Helens all the way in Ohio. Mount St. Helens is in Washington, for those of you that don't know. So this is these can spread very, very far. We talked about this. Okay, so let's talk about pyroclastic debris, the stuff that actually comes out of it, the rocky stuff that comes out of it. So we have our ash, which we've talked about. Ash is really, really small. 30 microns is a super, super small measurement. So they're very, very fine grained, and because they're fine grained, they can get up into the clouds, reach the stratosphere, and spread out over a long area. They can be carried by wind for miles and miles. So the real concern with ash is how far it can spread. We also have these things called lapilli, which are these really small fragments. Hands, you can hold them in your hand. They're very small, but they can spread out over a large area as well. And then we have blocks or bombs. These are anything larger than probably a soccer ball is going to be considered a block or a bomb. If there's enough force behind it, the volcano can bring up this size of rocks and just throw them for hundreds of meters. So if you're close to an earthquake, you may need to, if you're close to an eruption, you may need to worry about blocks or bombs falling on you. So one thing to keep in mind with when we have bombs, they're rounded and they're also still molten. So the block is where it's just part of the rock formation itself. It hasn't melted down. It's just debris that's been thrown out because of the explosion. The bomb is actually partially melted. Because it's partially melted, it has this more rounded circular shape. So that's why they call it a bomb. It looks like one of those old school cartoonish bombs where you have the wick sticking out of it. So these are pretty common, and they can weigh in the measurement of tons, so pretty big. Lapilli, cinders, this is where we're getting to the smaller stuff. It's usually pretty porous, so this is the same stuff that pumice is made of, tephra is made of. That's stuff that people used to use for its abrasive quality and still used today. So they're pretty small, but they can eventually form into pretty big rock formations. So you can have huge, huge fields of nothing but pumice rock formations, which are pretty cool. So the reason that we have these different types of pore spaces in pumice and scoria. Pumice is the felsic version, scoria is the basaltic version. So the easiest way to tell the difference between the two is scoria is always darker in color because it comes from basalt. Pumice is always lighter in color. Think of it, compare it to granite. Granite's a lighter color. So that is not Photoshop, that is a real picture. That guy is holding a piece of scoria because it has so much pore space in it. It's incredibly, incredibly light. So you can toss these things over your head, no problem. We call these things vesicles because they're not necessarily pores. Pores occur in every rock, but vesicles occur only whenever you have extremely rapid cooling. So all of these rocks were brought up to the surface from that explosion of the eruption, and they cooled so rapidly that air pockets formed all throughout the rock. So those are called vesicles. All right, so based on the size of these grains, what kind of rocks are A and B? What kind of pyroclastic material is A and B? So is it ash for A and lapilli? Is it lapilli and a block? Is it a block and lapilli? Is it lapilli and ash? Or is it ash and a block? B? Very good. That's right. Lapilli, we're still able to see the grain sizes. If it was ash, we couldn't see the grain sizes whatsoever. Blocks, they're anything larger than, let's say, a baseball. That'll be a good reference size. So blocks are going to be anything larger than that. So keep in mind, most geologists will use something for scale in their photos, and if they don't, they're a bad geologist. So the most common thing they use is a rock hammer. Rock hammer is just like the size of any other regular hammer that you have in your toolbox. So keep that in mind for when we're talking about size. All right, so ash. Ash is going to be anything smaller than 2 millimeters, really, really small, really fine grained. If this turns into a rock, we would call it a mudstone or a siltstone because we can't see the grains in it at all. That's how fine they are. So these are this really fine grained stuff, and it cools rapidly because as it's being brought up, it's exposed to the air, and since it's cooling rapidly, it hasn't had enough time to form into those lapilli, those pumice and scoria size rocks. So you have these tiny pieces of minerals, and some of these minerals can be quartz. So quartz is essentially glass. So imagine tiny microscopic particles of glass flying through the air. That's what we have when we have ash columns. So out of the three of these, which do you think is the deadliest? And this is more of an opinion. What do you think is the deadliest? But we do have some data to back up the actual answer. What do you think? That's true. It depends mostly on location. Very good. So what do you think? You think it's ash? Okay. What about you? Ash? Okay. Who all thinks ash? Who all thinks blocks or bombs? Who all thinks lapilli? So in general, ash is deadliest because it's going to kill the most people. Based on your location, if you're talking about you yourself, the person, and you were right next to the volcano, I would definitely say my biggest concern is a bomb and getting hit by one of those. But let's talk about the long-term effects of ash. So you can have structural damage from ash. If you think about your home and you get a lot of snow one year during the winter, there may be concern about your roof collapsing because of the actual weight of the snow. If you get enough snow built up on your roof will collapse. Your roof can only handle so much weight. Same thing with volcanic ash. As you can imagine, a lot of these volcanic areas, they're tropical. They don't have snow. Their roofs are meant for just rain, not prolonged periods of weight on top of it. So you add at least 5-6 feet of ash onto your roof, a lot of these houses are going to collapse. So you can get a lot of structural damage from this. Then the biggest thing is breathing in ash. So like I said, it's these tiny, it's not just smoke, it's tiny microscopic minerals. It's glass, it's feldspar, it's little rocks. And if you breathe those in, it's going to abrade your lungs. Those little microscopic particles are going to cut into your lungs and abrade your lungs. It can also do a lot of damage to cars and car engines. So if it's sucking into your air filter and your air filter isn't cleaned out, it'll corrode your engine. And it can break down pretty quickly too. So as you can imagine, if you need to rush someone to the hospital and the ambulance engine is full of ash and its engine is corroded, then that's going to be a problem. We also have the environmental impacts of ash. Since ash can spread over such a large area, it can enter waterways, and then you get something like a fish kill that you see to the left. Obviously, it can impact vegetation as well. It spreads out and just kind of chokes the soil, chokes the sun from certain vegetation. You can get crops that are devastated from ash columns. And obviously, if it spreads out far enough, you're not going to have enough food for livestock that requires grazing for their food. And as we mentioned before, they cover huge, huge amounts of area. So this is a map from a couple of different volcanic eruptions. So this dark circle in the center, that's from Long Valley. It's this huge caldera in Southern California. It's right near Mammoth Mountain. If any of you have skied in Southern California, it's one of the only places to ski there. We had Yellowstone 640,000 years ago. Yellowstone is located, that red blob right there, but look at the area it covered, all the way from Texas to North Dakota. That's crazy. And then Mount St. Helens, we had that huge column of ash that spread out laterally. That was a relatively small eruption compared to the other ones. Now you can detect microscopic ash all the way on the east coast from Mount St. Helens, but the real measurable ash columns are from Mount St. Helens all the way into probably Idaho. So still a few 100,000 square kilometers. So huge, huge areas. So if you would imagine an eruption, you'd think that it would spread out laterally in all directions. So why don't we have these centered in that particular eruption? Why is it the ash is spread differently than in all directions? Yeah. The wind. Yeah. We always have, if you look at the direction, it's all pretty much flowing from west to east. What else flows west to east in the continental United States? Think of meteorology. What's something that meteorologists talk about a lot? Do the words jet stream ring a bell with anyone? Yeah, so the jet stream we have, even though we have wind going all directions locally, the relative motion of all wind in the continental United States is flowing from west to east. And sometimes that jet stream dips down really far. That's why we get cold air from Canada and all the ice sheets up in the north. So that jet stream really dominates the direction that ash is going to be carried. All right, so let's talk about pyroclastic flows, which is absolutely the worst way to die, hands down. Maybe drowning. Maybe drowning's worse. I don't know. I was a lifeguard, so I think drowning's pretty bad. But pyroclastic flows are pretty awful. So they're super, super hot, as you can imagine. It's coming out of a volcano, so over 1,000 degrees Celsius, huge, huge amount of heat. And these can go up to 400 kilometers an hour. So there's no outrunning it. You can't even outdrive it. So if you're stuck near it, it's pretty devastating. The best thing you can do is get something in between you and the pyroclastic flow, like a building or another mountain. That would be better. But even then, if it has enough velocity, it can travel down the mountain, up the side of another mountain, and down the next side of the mountain. So sometimes they have enough momentum that even something as large as another mountain or another volcano can't stop it. So these cause the most damage because, as we've talked about, volcanic soil, it's very fertile. It's great for agriculture. People live near volcanoes because of that. So a lot of people live on these slopes for cultivating crops, and so they're the ones that get caught in these. So I mentioned the lateral blast of Mount St. Helens. This is what it looks like in real time. So you have this center of magma built up in that column in the center of the volcano, but you also have those vents that we mentioned. Fluids are going to follow the path of least resistance. So if we have a vent that's starting to grow and starting to get larger and larger and can hold a larger volume of magma, it's going to eventually break down the side of that mountain. So in the case of Mount St. Helens, what happened first was a collapse of the side of the mountain. There was a landslide on the side of the mountain. And what happens whenever we decrease pressure in terms of volcanoes and magma? What happens? If we release pressure from something, where is all that magma going to go? It's going to go out. So as we decrease that pressure on the side of the lateral side of the mountain, all of that gas, ash, that magma is going to follow the path of least resistance. It's going to go out laterally, just like a shotgun blast. So almost all of those forests that you see in the bottom of that picture were just wiped down, just knocked over clean like matchsticks. So there are some great photos of the aftermath of Mount St. Helens where there's just fields and fields and fields of dead trees, all knocked over in the same exact direction. There was so much force behind this blast. So another concern that you can have with these types of eruptions is something called a lahar. Off the top of my head, I don't know where that word comes from. I wish I did. That would have been a good thing to look up before class. I'll find out and I'll get back to you, because that's a weird word. But we can have regular landslides anywhere where we have moisture, unstable soil, and a hill slope. So if we have, imagine most of the rocks of the Cascades, not the rocks, the mountains of the Cascades region. They're covered in snow, right? Most of the year. So they're very high altitude, so they can have a snow cap for all year round. If you introduce gases, water vapor, magma, all that's over 1,000 degrees C, what's going to happen to those snow caps? They're going to melt really fast. So if you have a fast melting of these snow caps in this unstable soil on the slopes of these volcanoes, you can have a volcanic induced landslide. And that's what a lahar is. It's a landslide that's mixed with rock, it's debris from the eruption, sometimes it's gases, so it moves just like concrete. Think of concrete coming out of a concrete truck. Very fast, just a slurry of material, and it's very easy to get stuck in one. So this is an example of a mud flow that happened in Nevado del Ruiz, which is a stratovolcano. It's on the coast of Peru. Yes, Peru. So we get this massive amount of heat from the eruption, melting the mountain snowpack, and all of this races downhill. Everyone is living in the valley, of course, because that's where the land is flat. It's easy to build in flat areas. That's where people have always wanted to build, where they have to do less excavation. So it raced downhill, and imagine a wall of concrete, liquid concrete, just smashing into your house. It's going to take everything with it. So we had roughly 23,000 deaths, and out of 500,000 people living in this area. So it was a pretty devastating landslide just from this volcano. And they weren't even very close to the volcano. This volcano hadn't been active for 2 million years. And all of a sudden it had this eruption that disrupted all the snow on top of it. So it can happen anytime. Let's get this too. I'll post these in the canvas so you can watch them in your own time. It's better to see it with the sound as well. So we haven't even talked about the chemical hazards of volcanic eruptions. We know that we're building up volatiles in most of these explosive eruptions. Those volatiles have to go somewhere after they're at the surface, right? So we have CO2 and we have water vapor as most of the gas emissions, but we also have sulfur dioxide, SO2. And we also have sulfuric acid, H2S. So each of these can, it'll enter the stratosphere and it'll fall as acid rain, or sometimes it just enters waterways directly. So this can be really devastating. So Lake Nyos, that pictured on top in Cameroon, it's a crater lake, and all of these gases and hazardous materials and hazardous acids fell into this lake and just killed everything, all the way from fish down to any underwater vegetation. Everything is gone in that lake now. Same thing happened in nearby fields. We had this buildup of CO2 that took the place of a lot of oxygen. All those livestock just suffocated. They were standing on land. They were not close to the volcano. They were not under threat of any of the volcanic lava flows, but they were close enough that just this cloud of CO2 drifted downward, and they couldn't breathe. So not only did it affect people, it affected livestock. Not only did it affect livestock, it affected people as well. So 1,700 people suffocating from a cloud of CO2. All right, let's talk about shield volcanoes. What is this here? Hold on. Okay. We already talked about shield volcanoes. We don't need to discuss that a little bit, but we can mention Mauna Kea. So whenever we think of shield volcanoes, Mauna Kea in Hawaii is the best case example. The reason they call it a shield volcano is because it's large, it's round, it resembles shields that knights used to use back in the day. Rather than forming these pinnacled high peaks, they spread out over a large area. They're very, very gentle in their slope. But however, even though it's not forming a high peak, remember, this is the center of the ocean, center of the Pacific. If we measured it from the top of Mauna Kea down to the bottom of the ocean, it's super tall, 33,000 feet. That's a huge amount of magma built up over time. It took a long time to get there, but it's a huge, huge amount of material that's built up. So we consider it dormant right now. And the reason we know that is because we have seismic stations surrounding Mauna Kea. Hawaii is one of the best monitored locations in the world when it comes to volcanoes and seismic activity. Because of the studies that we do in Hawaii, we know a lot more about how earthquakes influence volcanic eruptions, how earthquakes precede volcanic eruptions, and how the two are related. So it's helped us a lot in monitoring and prevention and warning systems for other volcanoes around the world. So when we come to Hawaiian style eruptions, this is what they look like. So as you can see, it's kind of hard to see, but there are people standing just to the bottom of it, taking video and taking photos. This is not a violent eruption. This is very slow enough that you can stand there and watch it eat your house, basically, and film the whole thing without having to worry about anything. Now, there is still going to be some ash. There is still going to be some gases released, but we don't have near the amount of volatiles that we would in other eruptions. Remember, we're getting all that magma. This is a hot spot. We're bringing all that magma up from the interior of the Earth. We don't have enough volatiles to create these huge gases and gas clouds that would suffocate people and livestock. So the primary hazard here is going to be the lava flow, and it's more of an annoyance and a nuisance than anything else. If you live on Hawaii, number one, it's really expensive. Number two, you definitely need to get volcano insurance, and it is different than fire insurance, we have found out. But this is mainly what happens. You get flows that'll block roads. As you can imagine, if that can be problematic for emergency medical services. If you have to get somewhere and there is a field of lava in your way, you're going to have to reroute. And of course, electricity is another problem. So if you're going to burn down some electric wiring, that'll create new problems as well. So as I mentioned, we get some volatiles in this area, and most of those are not coming from the hotspot itself. But remember, that hotspot is going to be melting down the oceanic plate. So even though we're not pulling that plate beneath the asthenosphere, we're going to melt it down. We're going to agitate some of those volatiles. So right near the eruption in Mauna Kea, we have a little more than 50% of sulfur dioxide, which is pretty problematic. But because we can monitor these so well, we're able to map these out and get people to evacuate to areas with better air quality quickly. So there aren't any real deaths. But something that can happen is sulfur dioxide can contribute to smog. If we have regular sulfur dioxide from car exhaust, for example, we get smog. In this case, they call it VOG because it's from volcanic gases. So it's a smog that comes from volcanic air quality. And that's basically what it looks like, really hazy. Just like if you look at pictures of like LA, San Francisco in the 80s or the 70s, it's just all hazy. You can't even see a few blocks ahead of you because of all the smog. Similar to what we're going to see if we go to Hawaii and look at a live eruption. It's going to be very hazy. It's going to reduce the air quality. All right, tell you what, let's take a 10-minute break because this is a lot of information. So I'd rather you guys not get overloaded. So 10-minute break, take it easy for a bit.
I have a question. Do we have another exam in next Friday?
Alrighty, let's finish this up. So we talked about different types of volcanic landforms. We talked about shield volcanoes in Hawaii. This is an example of a shield volcano in Iceland. In those types of shield volcanoes, because we're right on a rift basin, we're going to form that general shield shape along that linear axis of the rift. So these are really long linear features rather than going in this large circle like we get in Hawaii. We get these long flows in either direction of the perpendicular to the axis of the rift basin. So just like in Hawaii, we're going to get basaltic magma, large quantities of it. We're going to get big buildup of these magmas. That's why the Mid-Atlantic Ridge is basically a mountain range underneath the ocean. But we're not going to get a really high explosivity of the eruption. So on a scale of 0 to 8 for the volcanic explosivity index, we're at a 0 to a 1. You may not even notice it, usually. You're not going to hear any loud rumbling, but there will be some release of gases, some ash, but not a lot of it. So Iceland's gotten really good at monitoring and working with these kind of eruptions. But we can get some flood basalts from these areas. So they may not have flood basalts now, but Iceland has had them in the past. And the reason we know that is because we have the geologic record of this. So whenever we get flood basalts, remember that's similar to a shield volcano, but we have huge volumes of it. So it just keeps coming and coming and coming until it spreads out over a large area. So in Giant's Causeway, which you have this in Northern Ireland, we have some of this in Iceland. Remember, at some point, those were together. They were closer together based on the plate tectonic shift. So we get this columnar jointing, and the way that these flood basalts cool, it creates this hexagonal shape. So it creates these really cool features that you can see in these columnar joints. There are some of these out in Idaho. If any of you are interested or plan on traveling out there, they're really cool because we had these huge flood basalts called the Columbia River flood basalts back there thousands and thousands of years ago. So you can still see these today out in Idaho, Eastern Oregon and Washington area. Pretty cool. So let's talk about flood basalts. So just like before, it's just like a shield volcano, but the magma chamber is huge. It has a huge capacity for that fresh magma to come up to the surface. And as you can imagine, way back when these were forming, and if you've seen these areas in the Columbia River Basin, it's pretty flat. You're not going to hit mountains until you get the Rockies or the Cascade Range. So it has nowhere to go but out and laterally. So it's going to spread out over a large area. So you can go all the way from Washington to the tip of northern Nevada, and you can see these deposits. They're huge deposits. So this formed around 16.7 million years ago to, this is about 10 million years of volcanism in this area. So like we said, huge volume of magma over a huge time period. And this was like from 350 different eruptions during that 10 million year period. So we think this is from a hotspot, a continental hotspot, and we think that same hotspot is underneath Yellowstone right now. So based on that recurrence interval, we have 16.7 million years to 2.3 million years to 1.3 million years to 640,000 years. We're still looking at a huge recurrence interval, huge amount of time in the recurrence interval. So do we have to worry? Maybe. We probably don't have to worry because we're on the East Coast. We may get ash flows and ash deposits, so we may have to worry about that. But in terms of the actual lava flows, probably not. So unless you plan on buying property near Yellowstone, I wouldn't be too concerned. All right, so let's talk about scoria cones or cinder cones. So these are really interesting, really cool volcanic landforms. So they're considered a volcano itself, but they're really small. They form really rapidly. They're pretty explosive, and they have really short lifespans. So just to create like a few hundred meters high cinder cone, it only takes like a month to a year. Really short period of time. So in most cases, these things do not exist where people have built up. And then all of a sudden, boom, this thing starts to form, and it kind of ruins everything in the surrounding area very quickly. So we have low viscosity in the magma. So we have these runny lava flows that'll spread out over a large area. Sometimes they can get blocked though and build up pressure because we have a high volatile content, lots of gas, so we get a lot more explosivity. So we can see those lava flows from the air, from spaceborne imagery. It's pretty easy to tell where it went and what direction it went. All those dark spots on the surface, that's where the lava flow came from. But they're still pretty small. I don't have a scale on this, but this is probably no more than 100 meters high, this little cinder cone here. So they're almost too perfect in their shape. They're like very oddly symmetrical, 33-degree angle slope, almost always a 33-degree angle slope. They have a lot of mafic magma, so basaltic magma. And because it's coming up in the continent though, it's getting some of that more viscous melt from surrounding parent rocks. So it's a little stickier, it's a little more viscous, but still is gonna flow out over a decently large area. So a really good example of this is Paracutin, Mexico. This is a very big corn agricultural area in Mexico. And in 1943, there was just this smoking crack in this cornfield. Nobody really thought anything of it. They were concerned about it because they didn't want any fires to ruin their corn yield. But then eventually it started erupting, and pretty violently, for 9 years, constantly, without stopping. And because of this is the youngest volcano in the Western Hemisphere. Like, it is only, how many years is that? 50s, like 70 something years old. Very, very young volcano. Like, the youngest rocks in the world are right there. But it eventually just enveloped the entire town. Everyone had to move pretty quickly. Now, this didn't really kill anybody, even though the explosions were violent, because it formed right in the middle of the cornfield, and pretty quickly, everyone was like, oh, this is a concern. So they evacuated pretty fast, but it just enveloped the entire town. So you can actually see, you can go there and see these, like their old cathedrals and large churches still peeking out over the lava flow deposits, which is pretty cool. But like we said, it has a really short lifespan. So it's completely inactive now. There's no magma there anymore. So it's completely gone. But they're so drastic in how quickly they form, how quickly they can change the landscape, that they become a really big problem for locals and farmers. So what type of magma do we have with cinder cones? We have viscous and low volatiles, viscous and high volatiles, low viscosity and high volatiles, or low viscosity and low volatiles. There's got to be a better way for me to ask these questions. There's just too many words. What do you guys think? Yeah. What was that? See? That's right. Low viscosity. We don't have a lot of felsic materials. We have some, but not a lot. So low viscosity, and we have a very, very high volatile amount because all that magma is melting down the surrounding rock, the stuff that has the water vapor in it, the CO2, all that stuff. Okay. So let's talk about lava domes. Lava domes are a little different than cinder cones. These can be a little more explosive if they get blocked. They build up in similar fashions to cinder cones, but once they become blocked, they can build up a lot of volatiles and pressure. So this is Mount Unsen, Japan, and this erupted in 1991. 12,000 people had to be evacuated. We had huge, huge pyroclastic flows, like you can see there. And look how fast that's moving down the mountain. Around 400 kilometers per hour. It's incredibly fast. So this was a really important eruption for the geological and volcanology community. A lot of the shots that you see in volcano documentaries and stuff come from the work of these few volcanologists that works in this area. They took a lot of data from that day, and they died because they were collecting data. And they were quoted with saying, "The problem with witnessing eruptions is that they are so fascinating, it's impossible for a volcanologist to not take more and more risks, and he doesn't notice it until it's too late." So 3 volcanologists died from this because these huge pyroclastic flows, they traveled a very, very long distance in a very short amount of time, and there's never enough time for you to evacuate and get away. But this is one of a really iconic eruption, just because it was one of the first times we had more recording power of it and more data to collect from it. So now we know a lot about these types of eruptions. So these are Palaean types of eruptions. They're about mid-range on the volcanic explosivity index, 3 to 4. We have high viscosity flows. Sometimes we get these small lava flows coming off the mountain, but the biggest problems with these are the pyroclastic flows, all the ash clouds, that avalanche of bombs and lapilli and ash just flowing down the mountain super, super fast. It resembles the shape of a stratovolcano, but they're a lot more different in their explosivity and their volcanic eruption styles. So these are named after Mount Pelée in Martinique. In 1902, they had a absolutely severe eruption. This entire town was devastated by this pyroclastic flow, much like in that video that you just saw. It swept down the mountain right into the sea and just devastated that entire coastline. About 30,000 people died in that. They were all caught in that pyroclastic flow. Like I said, worst way to die. They had no warning. There was no earthquake, no nothing, just a wall of ash, and they were all enveloped in minutes. Let's get that one. Yeah, let's keep moving. Okay, so now we're going to get into how a caldera forms. So a caldera is a remnant of a very, very explosive eruption. So the biggest portion of how calderas work is the volume of magma in the magma chamber. So we have a huge, huge amount of magma, and we erupt it all at once and we expel it. Now we have a void space in the center of the volcano. So after it's built up and has all this weight on top of it, you take away all this central mass. All that weight now has somewhere to go, and you get a collapse in the center. So as these calderas collapse, they're going to bring up steam. All their volatiles are going to come up. And eventually you get this massive crater. So Crater Lake is the best example of a caldera because we can see the entirety of the caldera itself. Even though that it's expelled all that magma from the initial eruption, new magma is coming up. So if you look at the center of Crater Lake, there's a stratovolcano starting to form. There's an island in the middle of that lake, and that's a fresh volcano starting to form. So it's going to continue to build up and build up until it may envelop the rest of that lake itself. The eruption that we had a few days ago in Hungatonga, those two islands are part of the crater that surrounds the greater volcanic chamber. So the volcano erupted from the center. It was an underwater eruption, but the underwater portion of that was the crater part. All the magma was situated right here, and the two islands were just the points of the crater that were above the surface of the water. So it was just like what we had in Crater Lake that we had a few days ago. All that magma in the center of that crater is what erupted. So for these, we have our highest viscosities because we have so much felsic and rhyolitic magma where we have the biggest amount of silicon content. We don't get a lot of lava flows, but we get more volatiles, so we get very, very explosive eruptions. So these just build up a lot of pressure because of the combination of high volatiles, high viscosity because of the silicon. So as this magma body is pushing up, you get uplift in the surrounding areas. And then as you melt and expel all that magma, you get that void space. All that uplift wants to sink back to where it was. So that's how you get the crater itself. So this is technically a type of a sinkhole, basically, where you have the removal of some mass underneath the surface, and all of that weight on the surface wants to sink down. Sinkholes that we get in eastern Pennsylvania happen similarly, but obviously there's no magma involved. There's just groundwater removing underlying soil and rock, so you get void spaces there. And then you get the collapse of everything overlying that void space. I am all too familiar with sinkholes. I had a sinkhole that almost swallowed my car whenever I was in my undergrad in front of my apartment. We had a sinkhole in front of our apartment, a sinkhole in the back of our apartment. So there was obviously a conduit following the two of them. So every morning I would pull out, I would check the parking spot, and it was always sunken. So it collapsed that and ate that parking spot at least 4 times while I lived there. I wish I had a video of it. It was huge. Okay. So we have Yellowstone as a caldera that we're looking at. We can't see anything really on the surface telling us that it's a caldera. Most people didn't even realize it was a caldera until probably 50 years ago. We knew there was some igneous activity there because we have these alkaline lakes, these very acidic lakes. We have mud volcanoes, which are these really small releases of pressure where you have all of this wet mud, all these gases bubbling up, and they pour out in these like real miniature volcanoes. They're no taller than maybe 3 feet tall. And then of course we have our geysers in Yellowstone. Yellowstone's very well known for geysers. So we know there was igneous activity, but we didn't know if there was an actual volcano located anywhere. So until we started doing geophysics and subsurface geology, that's where we learned how to map out and how to find these magma chambers and where these magma chambers are. All right, so just to review all the major types of volcanoes we've talked about today, just in case you forgot, because I threw a lot of information at you today. So if you need help with reviewing this and understanding this, I have office hours today. Please come to them. So we have shield volcanoes, low viscosity, basaltic magma, very low on the explosivity index, 0 to 1 on the VEI scale. Not explosive at all, build up gently, you get lava flows, spread out over large areas. Cinder cones, we have very short-lived, They're still low viscosity, but high volatile content, so they can be explosive. And they do have these long lava flows that can envelop cities. Stratovolcanoes, this is where we're getting our felsic magma, buildup of volatiles. The biggest volcanoes there are on planet Earth are stratovolcanoes. They're built up so high because of all that viscosity in their magmas. And they're the most explosive because the combination of highly viscous felsic magma with high volatile content, that's going to build up pressure, that's going to increase your explosivity. Lava domes, much like we had in Japan, we get a lot of pyroclastic flows with these. Very dangerous if you get caught in a pyroclastic flow. And of course, calderas, where we have so much of that explosive energy erupt out. You get that void space in the magma chamber, you get the collapse of it into a crater. So let's do a size comparison of what these kind of look like. So if we have, this is Mauna Loa on the island of Hawaii, the big island of Hawaii. This is the entire thing is the volcano. Whole thing is volcanically active. And it's huge. It covers a very, very wide area. And measured from the bottom of the ocean, it's pretty tall compared to the other ones. We have our stratovolcano of Mount Rainier down here to the left. Very high, very steep angles. Still overall, the shield volcano is much bigger if you measure from the bottom of the ocean, because all of it has been built up from that location. And then cinder cones, real small ones, real short-lived. Remember, they only build up for a month to a year. So on the geologic time scale, that's nothing. So they're really, really small, but they can build up very quickly. All right, so now we're getting to the hazard part. What do you do? How can you stop or prevent or predict or forecast or warn about volcanic eruptions? It's as with most things, it's dependent on three things: location, location, location. Where are you in comparison to the volcano? So are you on a plate tectonic boundary? Are you at a subduction zone? Are you near a divergent boundary? What kind of eruption are you going to have based on your location? How close is your population center? Are you in, for example, Mount Fuji? Are you right at the slopes of Mount Fuji? Or are you, say, in Delaware on the East Coast? Are you even remotely close to a volcano at all? Knowing what your potential hazards are. Are you going to get pyroclastic flows? Are you going to get lava flows? Are you going to get ash as your main concern? And how far is that hazard going to reach from that volcanic eruption? So let's look at the US. Most of our active volcanoes are on the West Coast. As you can imagine, the East Coast of the United States is tectonically dead. We do not have any active volcanism in the East Coast. The reason the Appalachians are so much smaller than the Rockies is because they haven't been built up for millions and millions of years. So they're some of the oldest mountains in the world, so they don't have any more volcanic activity, not really any faulting or anything else. So there's no real hazards when it comes to the Appalachians in terms of tectonics. But we do get some pretty frequent eruptions in the West Coast. So all of the Aleutian Islands, otherwise known as Nowhere, Alaska, nobody lives really in the Aleutian Islands. Those are all volcanic. That's a volcanic island arc. I think the last time people were there in great quantities was in World War II when the Japanese invaded those specific islands. Why they invaded those specific islands, I don't know. Seems to be a weird place, but oh well. Our biggest risk area, though, is Cascadia, all the way from Washington down to northern Cali. That's where we're going to get our greatest risk because we have huge population centers there, and we also have those active volcanoes in the Cascade Range. Also, we have our continental hotspots in Yellowstone. That's a risk. We can't really assess that risk just because the recurrence interval in between those eruptions is so vast. So we can't really assess, oh, is it going to erupt? Is there a chance that it's going to erupt next year? Sure. There's the same chance that it's going to erupt 10,000 years from now too. So we can't really do a lot of forecasting with that one. So what we do have is the USGS has been really good at setting up observatories. So the biggest one that we've set up is in Mauna Loa. That's where we get to learn the most about igneous activity, just because number one, it's so gentle. Number two, it's so active. It's constantly spewing out lava. So we can learn a lot about volcanic activity from Hawaii. One of our grad students in our department did her a lot of research at the Volcanic Observatory in Hawaii this past, when did she go? I think in November. So not a bad way to spend the cold months of November in Hawaii. So if you end up joining the field of geology, it will take you to pretty beautiful places. So keep that in mind. Okay, so remember how when we were talking about earthquakes, there's really no way of knowing when an earthquake is going to happen. For a volcano, we can tell when an eruption is going to occur. So as we know, as we're melting down the rock, we're going to destabilize that rock formation system. So any existing faults, they're going to get different stresses and strains built up, and they're going to shift, and they're going to tilt. They're going to be displaced. We're also going to get an increase in the actual ground. So we can measure the actual ground temperature. And if we get a rapid increase over a period of days, we can tell when an eruption is going to occur and give ample warning time for evacuation. So this is for Kilauea, for Kilauean eruptions. So we have data from thermal sensors all the way back from 1964 for a period of 2 years. And for each of those drop-offs, there was an eruption. So we can see there's a massive, it's pretty stable, and then all of a sudden there's this big rise in the temperature. As you can imagine, that's all that magma coming up to the surface. Then we get our eruption, we're ejecting all that magma, our ground temperature is going to fall again. So we go back down to our normal standard ground temperature. We're going to build back up again. So just measuring slope angle, measuring the thermal sensors, measuring all of these things can tell us when an eruption is going to occur. We can also measure tilt and the amount of deformation. As you can imagine, melting bodies of rock deforms the surface of the earth. So we can tell if there's a breaking point of that tilt or deformation, we'll be able to know when an eruption is going to occur. So this is from 2020. This is 2 days of data for the tilt in Kilauea. And this was right before it erupted in 2020. You get this massive tilt right around the 7th to the 8th. Huge amount of tilt. And then as it's erupting, we get back to a stable condition. We can also measure displacement, how much rocks have moved compared to its regular tectonic boundaries. So this is Eyjafjallajökull in 2010, that big Icelandic eruption. We had some pretty standard displacements, pretty normal for what you'd expect in a rift area. And then all of a sudden, around February, we start to rise drastically in displacement up until the eruption, and then we go back to normal because now there's nothing deforming the surface of the earth now. We're going back to normal. We're going to build up that magma chamber again. So some people have asked, can we use firefighters to prevent volcanic lava flows? You can. It's difficult. As you can imagine, a wall of lava is very hard, and if it's flowing very fast, you don't want to stand in front of it. And I would not blame you for not wanting to stand in front of it. But if you have slow moving lava flows, if you have really viscous lava that's not moving very fast, you can just hit it with hot water, cold water, get that rapid cooling, and you're going to solidify that rock at the front of it very quickly. So then all that lava will just build up kind of behind it and then kind of slow down, and you can really help halt the progress of it. It's difficult, but in certain cases you can do it. They could probably do this in Hawaii as well. So another thing we have to be concerned about is lahars and pyroclastic flows, but lahars in Iceland specifically, very, very cold area, lots of snow melt. So if we can look at our flood control systems, we can influence how lahars flow and prevent them from flowing into population centers. So Iceland has a lot of levees that they can block off or open up based on where those lahars are going to flow. And basically they can redirect it away from population centers, downslope into the ocean. And that'll help prevent any of those damages. So in summary, we cannot prevent volcanic eruptions, and the best thing you can do is not be in the area. So don't live up the slope of a volcano. If there's anything you take away from that class, I hope it's that. Don't live at the slope of a volcano. But it is important to know your area, know what kind of hazards you're going to get from that specific volcano, and the quickest evacuation route. And I think we're going to stop there. Yeah, that sounds good to me. So we'll pick it up tomorrow. We're going to be talking about rivers and flooding, which is probably the most widespread geologic hazard that a lot of people in this room have probably even experienced. So we'll talk about that tomorrow and Friday. Don't forget quiz 3 and your reading assessment due Friday. Keep an eye on Canvas. And yeah, have a great Wednesday, everybody.
Thank you.